So I think now we can move on to our, we're going to hear from our focus leads. We're going to give some context and demand. Of course, power doesn't exist unto itself. And so the LSIC has our focus areas, which are meant to um, inform each other. And so I think, let's see, who, Andrea, are you pushing all of the slides for the focus group leads? I believe you are.
Sure, they're coming up shortly.
Great, thank you so much. And I recognize that there are several questions that we couldn't get to. We can add, here we're going to add these questions that are not answered to the Confluence page so we can keep track of them. And as possible, bring them up again to the additional speakers. And they're also all saved. So we'll try to make sure that they're a part of the conversation that we can bring up again as relevant. And then most of these are also germane to additional talks and breakouts, topics in the breakout sessions. So, all right, first we're going to hear from Jorge Nunez on the dust mitigation considerations. Jorge, you can go ahead and take it away.
Great. I just want to do a quick audio check. Can you hear me okay?
You sound great.
Okay, great. Yeah, and I just wanted to quickly thank you, Wes, for inviting me to speak here at the Power Beam workshop. From the perspective here of the dust mitigation, and so as Wes mentioned, I'm the focus group lead facilitator for the dust mitigation focus group. And so my email is there below. And so we usually meet sort of the third Thursdays of every month. And we talk about, obviously, issues related to dust mitigation, including, surface power. And actually, at our last focus group meeting, I think last week, we had Wes featured, and we talked about some of the issues associated with, dust mitigation with surface power, and of course related to this workshop. So I'm really excited to talk to you about some of the considerations that we're thinking about. So if we can go to the next slide. So just kind of a quick crash course related to dust mitigation. And so, we're trying to take a picture, holistic picture. And so there's what we talk about, the integrated dust mitigation strategy, and the folks who have participating in our dust focus group meetings sort of have or aware of this or participating in this our workshop that we hosted earlier this year in February. And so the idea is really dust obviously is everywhere and it impacts every system. And of course, obviously, as we learned from Apollo, right, it can be pretty hazardous as well. And so we're looking at it from a holistic perspective, whereas not only for related to surface operations, and that includes EVAs, spacesuits, rovers, but also habitats, right? And so whether cabin filtration, airlock systems, dust detection, and then of course, ascent and descent systems, right? So including like, a human landing system, and of course, right, related to that, right, the plumes that are generated as a result of these systems landing and launching. But of course, also even, from orbital assets, right? So if you think about like Gateway, right, as the human landing system, returns to the orbital platform, right, there's going to be dust that's kicked up, pretty high up, as well as, if you have dust that's in the cabin, right, eventually that's probably going to get transferred. And so these are all things that we have to sort of consider. And so and that's why we're focusing on this sort of, integrated dust mitigation strategy. So next slide. And so from that, we've identified, technology areas that, are for concern, that things that, that are applicable to multiple systems, right? So for example, optical systems, thermal surfaces like radiators, fabrics. So if you think about spacesuits, mechanisms, right? So whether it's actuators or bearings or joints for robotic systems, seals and soft goods, right? So if you think about hatches and interfaces, filtration. So if you think for cabin, right? But also for ISRU processes, right? Where you have some gases. Then of course, surface modification. So whether it's landing pads, right? excavation and construction. And then of course, right, we added another one was related to isolation technologies. And so things, what are technologies available that we can help us keep out? And so I just put at the bottom there, right, you can sign up to join our focus group. And so there's a link there, as well as we have started standing up these subgroups that are related to these technologies areas. And we really welcome everybody to participate. So it's not just folks who are developing dust mitigation technologies, but we really want to hear from folks who are developing the systems as well, where, in terms of your needs for dust mitigation, and also how, foster collaborations of how some of the new technologies that are being developed, right, could get integrated into these systems. So if you move to the next slide, please. And so here's just some topics that I put here for considerations in terms of systems. Surface power, obviously this is focused on power beaming, and so here's some things that I thought, that are related. And of course, we have the vertical solar array technologies, right? So it's not only from surface generation, but how you get that power onto your other systems. And so here's some things that are systems and possible subsystems that are affected by lunar dust. So for example, if you have optical systems, so for example, if we just talked earlier about like laser beaming, and so your transmitters and your receivers, right? That especially with like laser sources, if you have dust, that's going to cause issues related to that. And of course, solar panels. Similarly, right, you're going to have thermal surfaces, right, radiators that may have dust that accumulates to that, and so you need to be able to control that. Similarly, right, mechanisms, right, if you're going to have beams that are going to be following your rover or something like that, right, those are areas that, dust is going to be play an issue, right. Similarly, right, if you're going to have tools, that's going to be critical, especially to maintain things dust free. And of course, surface modification, where like maybe that's something to consider, right? As you have your areas where you're going to be, your transmitter is going to be housed, so to minimize the amount of potential dust that gets kicked up. Okay, next slide.
And we're about at time, Jorge. So let's make sure that we have time.
So anyway,
thank you.
All right, thank you.
All right, wonderful. And these slides will be available after the workshop as well for everyone to see.
Mm-hmm.
And coming up next, let's see who's, we have Extreme Access. I don't know, I know Angela may have been running late. Oh, looks like she has just arrived. So, but we'll go ahead and go off, do Angela after this. We'll give her a moment to acclimate. So let's, we can start with Extreme Environments. So we have Dr. Ben Greenhagen, who's going to be telling us some relationship to that.
All right, great. Yeah, thanks, Wes. Can we go to the next slide? Yeah, so Extreme Environments, we're really focused on the challenges that come from the inherent lunar surface environment. And we've been going about this in a couple different ways. Because this is a pretty broad area of interest, we've broken our focus group up into subgroups right from the beginning. So most of our subgroups have been acting for a year or just about a year. And we've split them along the lines of kind of the major aspects of the lunar environment that could affect technology development. So we have radiation environment, regolith and surface interface, surface space weather and plasma environment, thermal and illumination environment, and vacuum and exosphere environment. Our subgroups are led by members of the community representing nonprofits, industry, and academia. And we do have a large effort in our focus group to put things on Confluence. So if you're interested in a particular aspect of the lunar environment, certainly encourage you to go check out our Confluence page, look at the subgroup information. All of them, in addition to gathering useful information, have also been working on community documents to help people understand the technology challenges of those environments a little bit more specific to whatever their technology needs are. I guess go to the next slide. All right, and then as kind of a larger focus group effort, one of the things we've been doing is trying to break down the idea of a lunar environment. The lunar environment is not a single environment. It's a whole bunch of different environments, and depending where you're going on the moon and when you're going, the technology challenges are going to be very different. So we've been looking at different aspects of the lunar surface environment and comparing them against what the description is in the NASA design specification for natural environments, or Disney document, and areas where that does a really good job of capturing them, and areas where we can help them capture them better. So to this end, for the past 6 months or so in our focus group, we've been talking about these 7 environments: 3 polar environments, permanently shadowed, areas of high illumination, and mixed polar environments, such as in a situation where you'd be going into and out of PSRs potentially. And then for non-polar environments, something similar to the Apollo-style near-side flat terrains, topographic margins, lunar pits and lava tubes, and surface anomalies. And you can see also all the environmental variations that we've been included in there. So also, if you go to Confluence, you'll see our thoughts on these different environments, the assessments of the subgroups, and what the specific environmental stressors are for each of these environments. And there's a lot of really good information there as well. And then go to my final slide. So I did want to just kind of shade this a little bit in terms of what the power beaming considerations could be as examples. We do have a number of folks from extreme environments that are participating today, and they'll probably be in the breakouts. So if you're thinking about thermal environment, one of the big questions you might ask is, are you designing for a diurnal thermal environment, such as you would have at non-polar latitudes, in which case you would have 14 days of light, 14 days of dark, very usual? Or is it something that's closer to the poles, and then you have a seasonal component? So you might have 3 months with very, very short eclipse periods, maybe only a couple of days, but then you will have 3 months where it's dark completely for 3 months. And for both your transmitters and receivers, those could be challenges. Permanently shadowed regions were already mentioned earlier by John. Surface charging, does it matter if your transmitters and receivers can handle these big differences in charging that happen when you're being illuminator and shadow? Regolith, this was also briefly touched on before. Do these things need to be on steep slopes? And the regolith might be less able to support structures. And then also, if you do have this power beam, could it be affecting the regolith around the receiver? And does that matter with the composition if it has things that have more iron or titanium, or volatiles or organics? And then finally, if there's any concerns from long-term exposure to galactic cosmic rays, or more frequent exposures to SEPs. So these are the types of things we think about. If there's any particular area of interest, I certainly encourage you to reach out to our group, and we can get you hooked up with the right people. Thanks.
Thank you, Ben. We're going to flip back to let Angela speak next. One thing that came up in a conversation that I had with someone who does terrestrial power systems the other day was induction, and that might also fold into the trade for long distance cabled solution as well, especially as we're traversing, magnetotail, where there can be extreme fluctuations. So great to have you here and participating. There'll be space to talk about all of these topics in the breakout sessions as well. And so now, Angela, if you're ready, you can go ahead and take over.
Sure, thanks. And thanks for flipping around, Ben. So hi, I'm Angela, and I'm the facilitator for Extreme Access. And in the Extreme Access focus area, mostly what we're concerned with is, allowing access to difficult places on the moon, or places that might be really hard to get to or hard to survive in, basically at any time that you might need it. So specific technical areas are listed here, things like mobility assets, navigation and hazard detection. How do you get to these places? Communication, avionics, autonomy, how do you navigate around the moon? And then Ben mentioned this a little bit, but we're particularly concerned with accessing areas that might be, in steep slopes or rocky terrains, or in the subsurface voids, and places like PSRs or long periods of darkness. That how do you access and survive there? And then another area that we are interested in is these long duration missions. So whether that's in the polar areas, where you have these areas that are really well lit, or in shadow for long periods of time, or at the equator where you're driving around, maybe following sunlight. So these are all areas that we're particularly concerned in. And I think there are a few areas that could really benefit from discussions of power beaming, or how might that help you access some of these areas. So if you go to the next slide, please. mobility is one of these areas that I think could be really benefited by power beaming, or getting us into these sort of hard to reach places. So, if we have a rover and a PSR, power beaming could provide benefits for that rover moving around, whether that rover is there purely for exploration or for something like excavation or ISRU. It's going to need power in those dark areas. And maybe we don't want long tethers down these steep rocky slopes. What other solutions might there be for that? Another place similarly is in these subsurface voids. A lot of solutions have tethers currently that people have been talking about, though there are some that don't. But can you do something with something at the surface, and not having to have a tether down across a rocky cliff? The normal sorts of things like surviving the lunar night or surviving in these areas at the poles that have these long periods of shadow. Or if you're there, perhaps maybe you have just a little bit of power. You just need a little to survive, and wait for the sun to come back. All of these things I think could be really beneficial for things when we have rovers and moving around on the surface. If you go to the next slide. There are some other types of trades that we've been looking at in extreme access. So having something like a way station, so a shed or a wadi has sort of various names of a service area that could provide survive the night capability and power and recharging. I think it's interesting to think about what sort of space that would cover in terms of power needs and what you could do instead with other solutions. So things like power beaming might give you a different amount of power, and is that enough, or do we need to have this sort of more built up infrastructure? These are still in discussion too. So there's this, I think really it's going to be sort of a multi-point solution. And so it's interesting to see what the different solutions provide in terms of long duration infrastructure on the moon. And next slide, please. And in the extreme access focus group this year, we're specifically focusing on permanently shadowed regions and also subsurface voids and lava tubes as areas that are difficult to access and have specific technology needs and testing. And I think both of these areas could really benefit from something like power beaming, whether that is for just getting there and moving or surviving once you're in there. And so I think we have several subgroups, much like extreme environments. And I think a lot of the other focus groups, we have broken discussions into several more focused subgroups and are looking at these two specific environments this year in general. And so if you're interested in that, are interested in those discussions, please, check out our Confluence page or reach out to me. And we would be happy to have discussions of, what we're doing here and what we're thinking and how we can be working with different power solutions. So I think that is all I have.
Great, thank you so much, Angela. And I think next is going to be Phoneme. If you're there, you can go ahead and take on.
Hi, can you hear me?
Yes, I hear you well.
Great, thank you. Thanks, Wes. My name is Athonu Chatterjee, and I am leading the excavation and construction focus group here at APL. Next slide, please. Yep, so brief introduction to our focus group. Our charter is to assist NASA in developing technologies that enable affordable, robust, autonomous construction of infrastructure on the lunar surface to establish a sustained human presence. So Dr. Mark Helberger from Langley is our NASA lead, and we have a great team here at APL comprising of experienced professionals like me and interns like Sebastian. So we have a very good group here at APL. So we meet on the last Fridays of every month. Our monthly meetings are held on the last Fridays of every month from 3 p.m. to 4 p.m. Eastern. Actually, we have a good talk coming up on tunneling and moon this month on July 30th. Tunneling is power intensive. So if you're interested, I encourage you to attend that monthly meeting on July 30th. We have a workshop coming on August 20th, as was mentioned before. And this workshop will lay out NASA's ENC roadmap. We are going to talk about some high TRL technologies for the initial infrastructure development. And power will also feature prominently in this workshop. So I encourage you to attend on August 20th from 2 p.m. at 2 p.m. Eastern, and it will be about 2 to 2.5 hour long workshop. And as you can see on the right, we have more than 500 groups of members in our focus group, and we have very good representation from industry, academia, government, and nonprofit. Next slide, please. So needless to mention, our ultimate goal is to build sustainable infrastructure, and this is a systems integration approach that encompasses all the focus groups. So in that bigger scheme of things, ENC technical focus areas is what you see here in this slide. We are focusing on some of the more critical infrastructural elements like landing and launch pads, habitats, both permanent habitats and in situ and deployable habitats, especially in the initial phases of exploration. Then of course, roads, berms. And later on, when we go to phase 3 or phase 4 of lunar-based development, we also talk about space architecture, urban planning. Then we have to build habitats that takes into consideration humanistic and aesthetic aspects of that takes into consideration these factors like humanistic and aesthetic aspects, because then we are talking about human beings staying there for a long time. So to build this infrastructure, these are the following technologies we are looking at in our focus group: additive construction, which is basically 3D printing or additive manufacturing on larger scales for building habitats, roads and landing pads and that kind of stuff. Then autonomous construction, high fidelity excavation tools specifically tailored for lunar application, and many manufacturing technologies, sintering being the most prominent of them, then regolith processing, additive manufacturing, and so on. And finally, when you are developing a lunar base, you will need repair and outfitting facilities. So we have also started thinking about how to maintain the infrastructure, spare parts, whether we want to make spare parts in situ or send them from Earth, and outfitting requirements. And that is an area we are getting into slowly. So as you can see, ENC activities are power intensive. Let's go to the next slide, please. So here's some ballpark numbers as far as power energy needs for ENC activities. Some of the ENC activities are concerned. One is excavation. NASA is working on continuous excavator technologies to account for the fact that we have very low gravity and hence very low traction force on Moon. So these are the power needs of some of the continuous excavators along with their capability. So we are talking about power requirements for an excavation capability of around 1,000 to 1,500 kg per hour in the ballpark of 200 to 500 watts. But the most power consuming aspect is the additive manufacturing methods that relies on melting the regolith, that is sintering. And in this case, we have listed some of the energy consumption numbers here for selective microwave sintering, laser melting. So as you can see, these are pretty power intensive. And all the more important is the fact that most of these excavators and there is a concept of lunar mobile paver that has the microwave, the sinterator, that is a laser sintering or the microwave sintering facility attached to it. These are all mobile. So they have to carry power supply, maybe a battery or solar power paraphernalia along with them. So there is some mass associated with that. So in that context, power beaming becomes very important, because by power beaming, you can reduce the mass of this mobile power generators. If you go to the next slide, please. So yeah, so power beaming for ENC, there are tremendous applications, and these were touched upon by John and Wes earlier. The killer app is in water generation in PSR. And there is one concept of operation I've shown here. This is from Sanders Lunar ISRU workshop. So you can imagine RASOR, which is an excavator, excavates raw material in PSR and delivers to a stationary water extraction unit. And in order to have a continuous operation without downtime, power binning will become extremely helpful here. And power binning in general could be beneficial for long distance mobile power intensive activities like road constructions, repairs, etc., where you don't have to carry, it lowers mass. You don't have to carry, say, a battery or a fuel cell and things like that. And power beaming could be accessed via something like charging stations along the roads. And it reduces the need for cabling, for wiring, long distance cabling and wiring, which are pretty intensive activities by themselves. And finally, looking way ahead, maybe in 2030s and 2040s, I can imagine a situation, I call it the power game, where lunar bases are well established, both by US and its allies and competitors. And then we will be vying for precious lunar resources, say, far away from the base. And then you will have to consolidate a rapid expeditionary forces to go there and maybe preemptively stake claim to that area. And in that case, power beaming will be indispensable. It reduces mass, it makes you more mobile, and your operations are more reliable. So with that, I end. Thank you.
Good, thank you, Athonu. That actually leads very well into ISRU. We're going to hear from Carl Hibbets, and I'll go ahead and let him take over.
All right, thank you. Can you hear me?
Yep, I hear you well, and you're
fantastic. Okay, so thank you again for the opportunity to speak. And Wes, I really like the bringing us in here because it emphasizes the system perspective of what you're trying to do here and what's natural to power beaming and getting power in general to these different areas. And so you kind of put it well, we're not really breaking through the stovepipes. We're trying to combine the stovepipes into one, and the closer we can do it to the stoves, the more effective we will be in building a system solution. So that's going to be the focus. What I discuss on is how to enable the power focus group to, do what you need to do to provide what we need for ISRU. So I should define ISRU, then I'll go to my one slide. And after I talk to my one slide, Michael Nord will give an overview on last year's supply and demand workshop, which will be a driver for power. Anyway, think everybody knows that for this purpose, ISRU is utilizing O2 from the regolith or water from the PSRs, both were for consumables, either for a propellant or for sustaining human presence, right? In order to, next slide, please. And in order to approach this, we've been, working for a year now, and we are realizing we want to break into separate breakout groups. We tried this in the beginning a little bit early, but now we realize we have 4 breakout groups that have been selected based off a survey that we had within the ISRU focus group. And you see these 4 here. And I'm going to talk to them from a perspective of maybe how the power focus group may be interested. So starting with water prospecting and mining. Basically, in this case, water in the PSR is not well understood right now. So in the ISRU focus group, we're realizing there's a gap for needing to understand the abundance, distribution, and form of ice in the PSRs. This gets to an earlier comment today, the need of power, perhaps science or exploration vehicles, maybe autonomous ones, maybe teleoperated or whatnot. So, we could need power there for that. And the ISRU focus group could perhaps provide information to the power group, ISRU focus group, to the power group about, these power needs, not only to power the rover, but to power the instrumentation as well, to make the measurements needed to characterize this water ice. So again, we are here to provide requirements and even metrics for the power focus group. Another aspect is that for water mining, and there are several different technologies that are being explored probably by members of the power focus group, because they're probably dual members with ISRU. And each of these approaches will have a different preference for the type of power, how the power is received, and how much power is needed, as well as what Michael will get to later is ultimately how much power is needed to extract enough water to provide the propellant needed that is expected to be needed, whether it's, 1 metric ton per year, or, who knows, right? Well, we do have ideas on that. Similarly, for O2 extraction and the creation of metals, of course, these have power requirements well, and there are different technologies as well being explored, and each one has a different power need and preference for the type of power, whether it's electrical power or solar power. Okay. And finally, this is something that was spoken to earlier in the chat quite a bit, I think, is the development of value chain development. How much is 40 kilowatts of power actually worth to you? And this gets to a system approach to ensuring that industry and government efforts are linked to the customer needs, and you understand who your customer is, and ensuring the right technology is being identified for development, including the right kind of power development and power distribution units. Okay, so yes, I do want to mention again, we are approaching this from a system perspective, so we're always interested in interfacing closely, not just with power group, but also the excavation construction and every other focus group within here, dust mitigation, et cetera. And finally, perhaps less relevant to the power focus group is laboratory facilities for ISRU. However, there's probably considerations there that I don't realize, so we're interested in interacting with the focus group in every way we can. Right. So this is just a quick overview of some areas where the ISRU focus group could potentially provide metrics and requirements to the power focus groups, and an overview of where we're going to be focusing ourselves for the next year. If Michael is available, I'd like him to speak to the last slide.
Great. Go ahead, Michael, you can go. And we'll get started on the next talk in just a couple minutes. So we'll slip a few minutes. Yeah. Thank you.
I'll go quick. As we started to ramp up this focus group, we kept running the same question over and over and over again, and that's how much. So to try to really pin that down instead of trying to come up with an answer ourselves, we decided to try and get together as broad a coalition as possible, industry, NASA, private industry, and to try and really understand what the demands and the supply were going to be. And if you take anything away from this, please go to the LSIC website. And if you're interested, it's all recorded there. You can check it out. We did a half-day workshop. We had several speakers on the demand side, several speakers on the supply side, and just some quick outbriefs. Looks like for ISRU, about 80% of the demand is going to be liquid oxygen. That's an expendable for almost every sort of rocket engine that we expect to land there, and it's usually the heaviest expendable. And we got demand numbers that were sort of anywhere from a ton at the bottom of the scale per year. SpaceX quoted a number of 100 tons for one of their starships. So I'll let you work your own math, how much extracting 100 tons of liquid oxygen and storing it would be on the moon. But we also, of course, looked at water ice and what some of the H2 supply issues might be. And we looked at several different technologies. I think what technology we're going to be using to extract either the water or the oxygen and metals from the regolith are still pretty wide open, but we had some great talks about those different technologies. So in the interest of time, I will go quiet and let the next speaker talk, but I do urge you to go to the website and take a look at some of the talks there if you are interested, or you could always contact Carl, Kirby, or I if you had any questions.
That's right. And if you need any of the contact information from any of these last speakers, focus group leads, you can find them all on the LSIC main page, or contact myself as well. Happy to put you in contact with who we have that might have the information that you need.